And then they say that the air inside the 2-liter bottle is, what did I say, 22? I don't know where I got 4. It's funny, the molar volume of a gas.
2-liter bottle?
Yeah. It's 2 liters, right? And then it's 22 degrees. And then the bottle is immersed in ice water.
1 liter, 1 liter.
Oh, it's 1 liter?
1 liter.
Oh, 1 liter. Okay. Sorry, automatically going to the 2-liter thing.
No 2 liters, so.
Yeah, exactly. Okay, so the 1 liter bottle, 22 degrees Celsius, and then you dip it in ice water. Okay, so I'm assuming that water with a bunch of ice in it at some sort of equilibrium state is going to be 0 degrees Celsius. So the first question is, does a net amount of air enter or leave the bottle? Okay, so yeah, actually it's important that you don't think of this as a 2-liter bottle. Or I mean like a soda bottle, or did they say soda? They didn't say soda bottle. Okay, let's assume that this bottle is like glass or something. Because if it's plastic and you stick it in, then it's going to squish and then air will come out. But if we assume it's glass or something solid, then air should go in. Right? Do you see why? Because once you put this in, as this air cools, what happens to it?
Gets smaller volume.
Yeah, the volume's going to be smaller, right? So then, how many moles of air enter or leave? Okay, so it's 20. Oh, let me see. Oh gosh, I got to deal with this fraction stuff. 1 mole of air is 22.4 liters at standard temperature and pressure. And then standard temperature, I know that's 0, right? And then pressure is 1 atmosphere? Okay. Standard temperature is 0, right? Yeah, because room temperature is like 20. Okay, so that's cool. So 1 mole of air is this. So then you can find out, if you flip this, you can, well, actually if you just divide this, you can find out how many moles there are per liter, right? So you get like whatever, 0, 0, or 0.05 or 0.005 or something like that. What does it come out to be? Okay,
Which part of it? The second part or the
if I just do 1 divided by 22.4, then I get 0.045 moles in 1 liter of gas. And that's at 0. Okay, so at 0, like if you just leave this here for a while until the air inside is 0, then there should be that many moles of gas inside, right? So then you just have to find out how many moles of gas are inside when it's at 22 degrees Celsius. Okay, so then, yeah, PV-nRT, that's what I would use. So then I would say N is equal to PV over RT. Now for this one, don't forget, for that T, what do you have to do?
Kelvin.
Yeah, make sure you use Kelvin. Because I think, if your R is Kelvin, right? I think 8.314 liters per mole Kelvin, I think that's in Kelvin, so just be consistent with yourself. All right. The pressures, and then if you use 8.314, that's atmospheres, so that's 1. And then the volume is 1, because we're looking for it at 22. This is 8.314.
8.34 is
Or is that wrong? Is that liter atmospheres? No?
I thought it was Pascals.
Is that Pascal?
No, that's
No?
joules over mole times Kelvin.
This is joules per mole Kelvin?
Yes.
Joules per mole
I'm
Kelvin?
nervous. I had it right.
Sorry, I gotta get the right constant here. Where did the volume go? The liter atmospheres one, is what, 0.08 or something? In chemistry, well, okay, if we use joules per mole Kelvin, where's your volume? Okay, because joules per mole Kelvin gets rid of this over here. And then the volume over here is because this is pressure, which is newtons per square meter times volume, which gives you newtons meters, and that's why they're both joules. Okay, so that's fine. So we just have to make sure.
So we don't use Pascal instead.
So this is going to be in cubic meters, because this is going to be pascals, and this is going to be in meters cubed. So then we have to be sure 1 liter is 0.0010, 0.001 cubic meters. So then it's just a matter of conversions. Okay, so then this, the with Kelvin, so 22 is 295 Kelvin. The pressure should be 1.01 times 10 to the 5th pascals, and the volume is 0.001 cubic meters. So that should work. This is to the 5th, and that should work out. So 1.01 times 10 to the 5th times 0.001 divided by, divided by 8.314 times 295. Okay, and so then I get, for this one, I get the number of moles, like the original number of moles is 0.041 moles. So then the answer is the delta N, if you will, is 0.004.
Isn't it 0.00?
Yeah. That's what I said, 0.004.
Oh.
Yes, you're correct.
I saw for the initial one I got 0.004.
You mean the initial moles?
Yeah.
So then you're, that means, do you do this right here? Is all your numbers the same as mine?
Yeah.
Okay, so those, you gathered all of them, right? All those boxes. Look in the drawers, look everywhere, and find all of those. And as I mentioned to you, under here are these plastic boxes. In these boxes are cubes. Yeah, they do look like that. Well, if we take a look, 1 times 10 to the 5th times this, you're going to get, that's 3, so it's going to be 100, right?
10.1.
Oh, 10.1. Wouldn't it be 1 times 10 to the 5th times 1 times 10 to the minus 3?
I'm missing a 0.
Oh, okay. So that's good. Very cool. Order of magnitude, no problem. What's an order of magnitude between friends? Yes? What? Sorry? You just found it? Oh. Okay, well, yeah. Dude, you're harshing my vibe. Let me get this problem done, then we'll take a look. But don't worry, I'm just joking around. All right, questions on this? So the issue is, which way does air go into this container? Why? Because when air cools, what happens to the volume? It decreases. I mean, if you take PV equals nRT and just solve it for V, it's pretty clear, right? That as T goes down, V goes down. All right, so As you put it in, the air inside cools, and which means air is going to get sucked in. How much? Well, you didn't have to do this. You could have just used this twice, right? Plug in once at the top stays the same, but the bottom just plug it in with the two temperatures, and then you'll get the delta. That's all. Where'd my screen thing go? Did it not record? It sucks a lot. Oh well, I guess I didn't record.